Ladies and gentlemen, good morning. My name is Daniel Sartell, and today our group, the Minesweepers, are here to present our findings from this past year's work. Now for our team introductions, we'll start over here.
Yep. I'm Cadet Jonathan Blake.
I'm Michael Berlin-Jerry.
Cadet Darius Satari.
Again, Cadet Sartell.
Cadet Glenn Hogan. Cadet Sam Huffman.
Cadet Jamin Hoffman.
Cadet Isaiah Velez.
So we can get into our agenda. So for our agenda, our first category for our agenda is going to kind of frame our problem and describe about our project overview. Our second kind of portion is kind of the real meat and potatoes of our presentation, covering the search pattern optimization, the vibration damper, the camera calibration, perception, flight testing, and heat map and post-processing. After that, we'll conclude with a little bit of future work and time open for questions. And with that, we'll get into the problem definition. So there are two halves that kind of frame this problem, right? There's the military component to it, and there's the humanitarian aspect to it. So for the military aspect to it, we see that a lot of contemporary conflicts, to include Russia and Ukraine, there's the vast employment of mines to prevent freedom of maneuver. Now, if we, as a friendly force, are afflicted by a minefield, we want to be able to accurately, safely, and efficiently navigate these minefields. We do have conventional means of doing so, but they are expensive, and so for that reason, we're here to try and propose a UAV option. For the other half of it is the humanitarian aspect. There are publications by the Human Rights Watch and from the Washington Post that provide a lot of evidence for the fact that Russians in their conflict with Ukraine are haphazardly placing these mines and delivering them from C-130s, and we see that there's a lasting effect of these being left behind because they don't track where they are, right? And so there are reports of farmers that will inevitably and accidentally run them over and die as a result. And so for the humanitarian aspect to it and helping to clean up after a conflict, we also want to suggest that too for a UAV option. With that being said, we'll get into the actual problem definition itself. So again, all that kind of describes and blends into our problem statement, which is about allowing kind of friendly ground units to safely navigate a minefield by employing an autonomous option, autonomous solution for that. And kind of the main kind of centralizing research question that began our studies was like, how do we employ an autonomous solution that can operate in abstract geometries and use sensors and then also kind of have user-imposed flight restricted areas? And I'll get into the project overview.
So the project starts with a soldier on the ground, or if not a soldier, some farmer, somebody that needs to clean out their field or some area with mines. And so to start with the Android Tactical Awareness Kit, the soldier, for instance, would go on here, map out an area in the map that they need to search, whether that includes search areas, no-fly zones, parts that are higher probability of mines, lower probability of mines, and then that's going to get uploaded to our ground control computer. From there, the ground control computer is going to compute a probabilistic search pattern that's ideal for whatever situation it is. It's going to be different every time this program is run, and it's going to optimize the search pattern for that specific situation. From there, that's going to be sent to our onboard computer on the drone. Those CSV coordinates, a CSV file with grid coordinates for the drone to fly are going to be flown autonomously by the drone itself, detecting mines as it goes. It's going to then save those mine locations to a file, send it back to the ground control station, do some math on the back end, and display on the ATAC not only a path through the minefield, but also locations of the mines in the minefield itself. In the flight, the software storyboard defines what's going on. So we're doing on-the-edge computing. As we're flying, we're seeing the mines on the ground, getting the mine pixel locations in the camera frame, and then doing a coordinate transformation from the pixel frame to the real-world frame. So if I know where my drone is, where I'm oriented, roll, pitch, yaw of the drone, and I know where I'm seeing that mine, I can then do a coordinate transformation to predict where that actual mine will be in the real world. We then save these into a file, and that's what gets sent to the ground control station at the end, where post-processing is done and the output is given to the soldier or farmer or whoever civilian needs to clean through that minefield.
To go off of what Cadet Hogan was talking about, our algorithm takes in user-defined boundary points of the search domain, any no-fly zones, and areas of greater probability. Once that is taken in, a particle filter is overlaid onto the search domain, where each particle is representative of the probability of a mine being there. So the greater the particle size, the higher the probability of a mine being there. The smaller the size, the less the probability of the mine being there. Once that is all initialized, the drone begins searching for mines and it's drawn towards the heaviest probability particle. So it goes towards that, and then it's also based on the current trajectory of the drone to maintain efficient path. Additionally, there's a adaptable search radius. And what I mean by that is there is a circle or a radius around the drone. The drone only searches for particles within that search radius. This is to allow more efficient path planning. What that search radius does is it's based on the local probability density of the particles in the area. So if there is a high probability of a drone or a mine being there in the area, the search radius will close and get smaller. This is to allow the drone to spend more time searching in that area. If there's not a lot of probability in the area, the adaptable search radius will increase, which will allow the drone to find the next highest probability or most efficient area to search next.
Perfect. All right. So one of the major issues that we saw from last year was the group had used a rigid mounting system for their camera, and so as we can see here from this small clip of the video footage, we had a warping of the video footage, and we call that term jello. Excuse me. And so in order to enable our AI visualization detection algorithm that will be spoken upon later, we had to devise and design a new camera mount that could reduce the effect of this warping and vibration. So the solution is seen in the middle portion right there. You can see the camera. The most kind of important component were the wire vibration dampers that we can see on the side, and the wire clampers with screws and washers that hold it together. And so in order to actually validate the design, we did a lot of vibration testing, which we talked about right now.
Right, so before we actually put this on the drone, we wanted to make sure that it would attenuate the frequencies that drones would emit. And we know that drones usually emit high frequencies ranging between 80 to 100 hertz. So we were looking for something that actually did well when the input frequency was really high. So when we took the Fourier transform, we looked at the output frequency from our vibration damper, and we saw that as frequencies increase, the magnitude in decibels of the output frequency actually decreased. So we knew that it did well when under higher frequencies, so we thought this would be a good design to put on our drone.
So the artificial intelligence visualization algorithm that we are using is called YOLO. It's you only look once. And how this works is we're going to capture a frame. We use our YOLO detection, which just takes a look at the stop sign and it'll visualize that object and place a green box around it. We then take our pixel from the very center of the object, and that will be uploaded and then further changed from a 2D coordinate to a 3D grid GPS system. Something to note here is that we are using stop signs instead of mines. However, this is a plug-and-play system. We wanted a proof of concept. We didn't have the time to go through and create the entire visualization of detecting mines and going through and making that possible. So we have just our proof of concept and how it will work.
So going to camera calibration. So okay, thank you. So going to camera calibration, what this is doing is we're taking the 2D picture coordinates of the camera and we're translating it to where we predict the 3D real world coordinates of the landmine is going to be. So to do this, we need to find the intrinsic matrix of the camera, and we do this by doing a series of calibration tests using a checkerboard in order to have the camera be able to accurately locate an object. Then we translate that, send that K value that we find right here, and we send it to the landmine localization algorithm, which will be used to detect where we predict the landmines are going to be located at.
So the next step is actually flying the path. So the first thing we're going to do is simulate the path in that flight path generation on the ground control computer. From that computer, we're going to pass that on to the actual onboard computer on the drone itself. Something to note, this isn't done by a pre-programmed software or anything. We're not uploading a path to QGC or Pixhawk, if somebody knows what that is. We're actually putting it onto the computer itself, which is talking over robotic operating system through Mavlink, giving the flight controller commands to go to this specific grid coordinate, and then on and on, we're continuously doing that as it flies the path. So once it starts flying, the drone is flying on its own, continuing the whole path by itself. Looking at the air analysis of how well we're flying this path, this is an overlay of our desired path versus the actual path we flew from our log data. And we have a pretty good mean and standard deviation of 0.15 meters with 0.11 standard deviation.
Okay, so getting into actually finding out where the mines are, we had a robot operating system or ROS node running.
which took a live script and it would localize where the mines are in real time. So that used JT Cadet Blake's his intrinsic matrix to then take the pose, yaw, pitch and roll, altitude, and GPS location of our drone, along with rotation matrices to transform that into 3D space and plot the landmines. So what we wanted to look at is if using the intrinsic matrix or if using the camera specifications that come from the data sheet of the specific camera we're looking for, which one would work better. We found that actually using the intrinsic matrix of the camera, which can be tested for any camera on the market or any camera you have, perform better by about 0.1 meters. And also it's just a higher level technique that can be more generalized to this design. Getting into the actual path generation for soldiers to walk through. When the live script runs on the drone, we get the drone locations and the certainty of the mine locations. Those are then pulled from the drone back to the ground station, and a heat map is created where you have yellow being the most certain points of where the mines may be, and then it diffuses out to black, meaning there's no mine there. From there, we extract the centroids from the middle of these heat maps, and then we then plot them to see where projected mine values are. And we run a gradient descent algorithm on this heat map. Imagine the heat map becomes a contour where you roll a ball down a hill, and the ball will take the path of least resistance. That's the path that's being generated in that animation right there, and you can see it's avoiding all the projected mines. From there, this path is then saved to a CSV, exported to this ATAC software, and that is then the path that the soldier will take. Now, an edge case I want to go over is if we have a no-fly zone that we set, the way we're going to mitigate that is that we turn the no-fly zone into an area of mines. So in this test, we had 3 mines labeled mine 1, mine 2, and mine 3. And then this is the no-fly zone right here. You can see that we overlaid mines over this no-fly zone that is taken from ATAC. And then when we actually go to do the plotting, you can see that the path on the right avoids the no-fly zone because it's treating it just like you would treat any other landmine. This is a video demonstrating kind of the start to end use of this project.
One trooper team is on standby.
Right now, setting fly zones and no fly zones.
Sweet. All right, we have a handful of options for future work for the countermine research team. The first thing is for YOLO detection, possibly getting upgraded capabilities on the visual camera and also thermal detection for detecting mines that may be thermally activated. The second thing is to reduce camera error. So with the drone estimating where the mine is, there are improvements we can make in its accuracy on that. Thirdly, for LiDAR, for collision avoidance, this will allow us to fly the drone in areas that are much more contested or have trees or other obstacles or buildings, and that would prevent the drone from bumping into anything and then defeating the operation. For mine trigger mechanism, there is also the option of having the drone be able to drop or deploy some sort of something that will trigger the mine. So instead of just detecting it, it can also detect and physically clear the field. Then the next improvement to be made is to have the calculations be computed on the drone in flight while it's flying. Then to improve algorithms for the edges and terrain when it's flying near the no-fly zone edges or on rougher or hillier terrain, it can get a better estimation based on knowing its own altitude and where everything else is. And then lastly, it could possibly use one or more drones with it, and you could have a cooperative swarm kind of function where the drones are functioning at the same time scanning the same field. This would obviously be a bit more rigorous since you'd have to have parallel task execution where the drones are not overstepping each other and are all doing the same thing in their own areas.
And this concludes our brief. We'd now like to open up the floor to any questions.